Yeah, Don Gooker University of Iowa, where I've been there for the last 16 years, and prior to that, University of Missouri for the same amount of time. So I've been in the business for a while and seen a lot of change, but nothing like we're seeing right now with the impact on technology. Obviously, it's on your mind. These are your responses, some of your responses from the pre-conference survey that relate to technology and change and data. So let's start with the chessboard and the game of chess and the legend of the king and the inventor of the chess game. The king was so impressed with the inventor that he granted the inventor any wish that he wanted. And the inventor said, I just want enough grains of rice to feed my family. And the king says, no problem with that. That's an easy one. How much do you want? And the inventor said, well, I'd like you to place 1 grain of rice on the first square and then double it with each subsequent square. So on day 2, 2 grains, day 3, 4, 4 became 8, 8 became 16, 16 became 32, and by the time you're on the 64th block, you're at 18 quintillion grains of rice. And this notion about exponential change is what this demonstrates. And so we're looking at, as it relates to technology, when we look over the last 10 years and we look into the next 10 years, we're on the second half of this chessboard as termed by in the Second Machine Age, book by Eric Bornjolfsson and Andrew McAfee, who termed this. They were from MIT. So there's this notion when we talk about change, keep in mind, we're talking exponential when it relates to technology. We're going to get into that a little bit deeper. Jack Welch, former CEO of General Electric, approached change organizationally. And this is a quote that I've lived by for many, many years. And Jack was in a different time and place. He wasn't dealing with accelerating change. He was dealing with our normal linear change. But he says if the rate of change on the outside of your organization exceeds the rate of change on the inside of your organization, the end is near. Meaning that organization, you got to pay attention on what's going on the outside and keep pace with that change, or else you're going to be consumed by it. And so today's session is to get us thinking about that change. And so to that end, let's cue up this. So you can see, first of all, this is produced from Scotland, but it has international applications. And secondly, there's a ton of stuff packed into this 2-minute video. In fact, I am involved in presenting a full-day workshop through APA on the changes that were touched upon, including the last one, to become more human. It speaks to the the soft skills that I was talking about earlier, because as the machine becomes more and more competent, it's the creative, it's the non-machine skills that are going to be more important. But one of the things that, to keep it to 20 minutes here, is this takeaway. Technological change is picking up speed, but human capacity is struggling to keep pace with it. We're used to thinking linearly, not exponentially. So I'm going to give you another example of exponential change, and it deals with the example of the lily pond. And in 30 days, the pond's going to be completely covered with lily pads, and on day 1, we have 1 lily pad, and it doubles each day. So when will this, on day 20, when do you think, what percentage of this pond is going to be covered? If day 30 is fully covered, and day 1 it just has 1 pad, where are we at on day 20? 50% or more? Anyone? 25? 5? The answer is less than 1%. It's just a fraction that's covered on day 20. How much of the pond is covered on day 29? Half of it, because it's exponential. And this is easier to get your head around when you see a graph like this, and you can see how low we would be on day 20. Well, if we applied this to organizations, what day do you think Kodak woke up, or Blockbuster, or some of these companies that realized the world changed on them and they were too late to react to it? What day is the taxi industry on right now? They're trying to adapt and borrow the models of Uber and Lyft, but they're probably on day 28. The end could be coming soon. So the relevance of that, and to get to this graph, is to think about this. This all started the modern era that we're in right now, the iPhone. A little over 10 years ago, it was launched. So was Watson. So was 4G. So were all these other technologies. Facebook was earlier, but were coming of age during that period of time. Airbnb, all these didn't exist prior to 2007, except for Facebook, but it wasn't commercialized. The ones you may not be familiar with, Palantir, Hadoop, GitHub, and all that, were the fuel, were the engine for the technological explosion that we're dealing with and making this exponential change happen. These technologies work together in an integrated fashion. So if you look at where we're at right now, and you look at the second half of the chessboard, back to that, can you imagine where we're going to be in 2027? We're already entering that second half of the chessboard. Blockchain, 5G, big game changers. 5G is over 10 times the speed of data transfer than 4G. And it's just going to open up all kinds of opportunities and possibilities for the facilities world. So again, these technologies, what's different than pre-07, these technologies are working in an integrated way, adding fuel to each other. And so no better example than big data, where exponential growth in volume and variety and velocity have come together to launch the big data revolution and bring us to the Internet of Things. And who are we? We are the manager of things. The Internet of Things is ours to manage and deal with. So let's take these one at a time. Velocity, Gordon Moore, Intel CEO, 50 years ago in the 70s, predicted that the speed of the integrated circuit of data processing would double every year for 10 years. He was almost right. It doubles almost every 2 years, but it's been happening for 50 years, and there's no end in sight. And in fact, I should have pointed out in that previous slide, there was an icon up there on material science. Got to keep in mind what material science breakthroughs are doing for the speed of all this technology, for the enabling of all this technology. And in fact, what's interesting, when you look at the second half of the chessboard, there's now material science breakthroughs that have self-healing concrete, as an example. Have you heard about this? That they embed a bacteria inside concrete, and when the concrete cracks open, the bacteria starts producing a bonding agent with a calcium, I'm not a chemist, but whatever is bonding chemically with the concrete. So the material science has fueled this. This is why data centers have become enabled, because we've figured out how to keep them from producing the heat that we thought was going to be their limitation. But anyhow, velocity is increasing, then we get to volume, the ability to store this data and use this data in an efficient way. It's doubling about every 2 years as well. You can see that where we're at in 2018 and where we're going to be in 2020 and where we've come from. So we no longer have limitations on data volume or data storage or data access. The third piece of that big data gets to the Internet of Things. It's the things that are connected now. Sensing technology, sensors have dropped through the floor. They're tens of dollars instead of thousands of dollars. So we're putting them on everything, and they're everywhere. And we have a huge amount of sensors on our campus that we're not even aware of. Our pilot project for Fault Detection Diagnostics, that I'll talk about in a minute, has 23,000 sensing points in it that we could use, but more importantly, chose not to use most of those. But that just gives you some idea of scale of sensing technology that's hitting our world. So this gets to the Internet of Things, and I'll talk a little bit about really the first application of IoT that's really grabbing hold of our industry. So if we think about those 23,000 sensing points that I just mentioned, break it down into 8 categories, brings us to this slide that IBM has produced. And I'm going to key on the HVAC one and go to one example of an air handling unit that has 25 sensing points. You don't have to read this, just know that there's 25 sensors or so related to this, and this is what it's watching. This is what it's sensing, and this is what it's picking up in what are very small time increments, capturing this data on an ongoing basis. But what it's telling us is this. This is the application of fault detection and diagnostics, where we can predict that something is going to go wrong with our facilities before it occurs, because something is falling out of the boundaries of predicted or normal operation. So maybe the best way to sense this, so it's different than our alarm systems that we've traditionally had in our mechanical control systems. This is looking at trending data. So how many engineers in the room? There's a fair amount. Every one of us should have had this in one of our classes in engineering curriculum. This is a PFP curve, or PFF curve, potential failure curve. Every mechanical system eventually fails, and that's the curve that goes down to complete failure. But what's important is these early warning signals that are out there to predict that we're on a failure curve. And currently, we get alarmed when we cross one of those points. We don't detect a trend. This is what Tom Freeman in this book, On the Age of Accelerations, talks about as weak signals. Our institutional knowledge, our mechanics in the building pick it up at audible noise or smell or vibration. They got the feel for it. That's why we value institutional knowledge. But technology is going to displace that human institutional knowledge because it's going to get us into the earlier predictive warning signs that are out there. The business case for this, as you can see, the longer you take to detect that failure, the more costly it is to deal with it, whether it's the actual cost of a repair or the disruption in what would otherwise be planned work. So predictive maintenance vis-a-vis the fault detection diagnostic application is moving us to a planned maintenance world, a predictive maintenance world, a more cost savings world. Instead of funding us for repairs, the money needs to flip into the enabling technology to avoid those repairs. So I think the auto industry offers a good example. I'll run through this quickly. This is my 62 Chevy back in the day. I could fix everything on it. Not that mechanically inclined, but it wasn't that complicated a piece of equipment. That's what we're running today. If you have the building analysis. But then soon it became that you needed a technician and you needed the technical equipment to monitor the building. We entered the digital world with that. And then we're seeing augmented intelligence, where humans are working with the intelligence that's on our automobiles. And believe me, automobiles are a very sophisticated piece of equipment. Again, think of our buildings following a similar trend lines. And then we get to artificial intelligence, where the intelligence just takes over. It could actually be safer in situations. So if we thought about the automobile and what is condition-based maintenance, my 62 Chevy, my car 10 years ago, I was changing the oil every so often and after every so prescribed miles, religiously. My new car that I bought just a couple years ago is doing condition monitoring. It's telling me when I have to replace that oil, and I'm replacing that oil with a lot more miles and a lot more time behind me than I was initially comfortable with. I was almost not trusting it was telling me, because it was going way too long to change the oil. But the point being, it's monitoring the condition of the oil based on my particular driving habits and my climate and so on and so forth. And that's a much more efficient way to deal with it than a scheduled PM program. So again, think of your building PM programs, how much waste there could really be in that, because we're following industry statistical norms that are conservative for dealing with equipment condition rather than sensing predictive tools that could have us dealing with that equipment 1/3 of the time. This also leads us to continuous commissioning, where we're using the technology to hold the operation optimization of our facilities constant. So when something starts to drift out of performance, a fan starts slowing down, a filter starts getting dirty, we get that warning, we get that report that we need to go out and deal with it, and we move along maintaining a level of performance, rather than this sawtooth recommissioning curve where, again, the old automobile analogy where the car's going out of tune, you need to take it in the shop and get it retuned. This is getting it optimized and then holding it. But what's even better is now that you have a systems look at what's going on, you can find new opportunities to increase performance just by the diagnostics that the Fault Detection Diagnostics brings to the table. So there's this opportunity to actually elevate the performance of the facility. So I guess what we do will change, and how we do it will change even more. And let's look at this.
Hey.
Pass, please.
I'm here to fix the elevator.
Nothing's wrong with the elevator.
Right.
But you want to fix it.
Right.
So who sent you?
New guy.
What new guy?
Watson.
My analysis of sensor and maintenance data indicates elevator 3 will malfunction in 2 days.
There you go.
You still need a pass.
Some things, not all things change. You still need a pass. But this speaks to Watson. Now, Watson gets us to a real interesting place, and that's cognitive computing. That's machine learning. That's the building of artificial intelligence. What Watson can do is it can understand the English language and learn from it, self-learn. Watson competed in Jeopardy and beat everybody out because it studied the collective body of everything in preparation for the Jeopardy game. And so what this leads to is, again, machine learning that over time will displace even our analysis of the fault detection diagnostics data that we're interpreting. So it's a really interesting world that's ahead of us. Right now, the mainstream, I'll call it, application of big data is fault detection diagnostics, but the next level is we'll start this, the machine will be understanding what the problem is and how to fix it. In fact, blockchain might enable a corporation, a company like Train, to actually operate the chillers for us, and based on their worldwide history of problems and solutions, apply that, not based on a few examples, but the collective industry solution. So it's a really interesting world, and I'm going to end with one more video that kind of pulls this all together. It's produced out of Ireland, but we'll wrap up with that.
We're surrounded by the Internet of Things. Thousands of sensors relaying data from cars, factories and stores. These sensors and the data they produce ensure safe driving, food safety and efficient production. However, there is much more we can do with the large amounts of information that is generated. At IBM Research, we're developing AI technologies to connect and understand data in ways never seen before. We combine machine learning with knowledge graph reasoning to enhance the data with layers of semantic abstraction. This gives us new, natural user interfaces that allow us to gain new insights from the data.
A lot of the data that's coming from us is IoT based, and that's Internet of Things based, so that's machine to machine data. When you get a lot of data thrown at you, it ends up being a very difficult task of trying to extract real insight from that data set. The only way we're going to solve this problem is to teach the machines to make sense of the data so we can ask it questions and expect reasonable answers.
We developed a knowledge graph for IoT. The system knows all about IoT and understands the meaning of different types of data. It works in a similar way to the way our brains think. Imagine a temperature sensor in a building. An office worker tells the system, "Hey, it's too hot in here." It analyzes the speech as text and extracts the concepts hot and here. It understands that hot is a concept for heat. It quickly accesses the knowledge graph to find all assets in the area. It then uses AI analytics and sensor data to determine if the temperature is actually too high. It realizes the office area is located close to a window. It checks the illumination sensor, automatic blinds and weather to see if there is high sunlight causing excessive temperature and finds nothing unusual. It tries a different branch in its knowledge graph. It finds an AC unit and uses AI diagnostics to find that the heating valve is switched on. So it can actually identify the problem and then commission work automatically to the relevant people to go and fix that problem.
It is a scalable solution that enables IoT to learn behavior, to understand operation and to self-diagnose problems, while making human-machine interaction more natural and intuitive.
It's a general-purpose, artificially intelligent, multi-dimensional knowledge graph for IoT. It combines reasoning with machine learning to analyze and understand very large data sets in real time. This enables new insight from complex systems at scale.
So can you imagine what the world will be like a decade from now, what our profession will be like? So with that, welcome to the second half of the chessboard, and thank you for your time.